Hello everyone, it's Mr. Bowman. We are going to continue our discussion of random variables in this video by talking about continuous random variables. But before we do that, I'd like to review the idea of a random variable in general and the idea of discrete random variables. Random variables are quantitative or numerical values that a variable can take on based on some random phenomenon. So for example, let's say we're rolling a die and we want the random variable to represent the number that comes up on the die. So there are some restrictions on that. Each of the probabilities associated with each of the individual outcomes has to be a number from 0 to 1 inclusive, and the sum of the probabilities has to be equal to 1 for all the outcomes in the sample space. It's considered discrete because there's a finite or countable number of outcomes. What we'd like to do today in this video is to talk about the idea of a random variable, but a random variable with an infinite number of possible outcomes. So we're going to start our discussion with a simple example of a discrete random variable, and then we're going to transform that, so to speak, into a continuous random variable. So let's say the random variable represents the weight of a baby to the nearest pound, and we know from our data set that the range of weights could be from 5 to 9 pounds. So the values in that sample space could be 5, 6, 7, 8, and 9. And based on our data, there would be a certain probability associated with each of those outcomes. So it's possible, for example, that the probability that a baby weighs 5 pounds is 13%. So how would we interpret that? We would interpret that as saying, based on our data, the relative frequency of 5-pound babies is 13%, or the probability of a baby being born that is 5 pounds is 13% based on our data. So we might have a histogram for the distribution of baby weights that look something like this. Take a look at this histogram and take a look at the two questions below it and take a moment to answer those questions. So the total area of the rectangles in this example would represent the total probabilities for all the possible outcomes, which obviously is the total probability for all the outcomes in the sample space, so that would be equal to 1. Specifically, the area above rectangle 7 would represent the relative frequency of babies being born that weigh 7 pounds, or our estimated probability of a 7-pound baby. Suppose instead of weighing babies to the nearest pound, we decide to weigh babies to the nearest tenth of a pound. Think for a moment about what that would do to the probability distribution and the histogram above. If you imagined a probability distribution still ranging from 5 to 9 pounds with 10 times as many outcomes, you are correct. And the probability histogram might look something like this, with a whole bunch of very narrow rectangles representing the various possible weights. As with any other probability distribution, the sum of the probabilities would be equal to 1, and that means that the total area of the bars that make up this histogram is also equal to 1. So if we wanted to estimate the probability that the baby's weight is more than 7.3 pounds, what we would do is we would go up to approximately 7.3 on our probability histogram, shade the area that represents more than 7.3 pounds, and estimate that. I would estimate this shaded area to the right of 7.3 as approximately 25 to 35% of the distribution. So again, interpreting that in context, that would mean that I would estimate the probability of a baby being born that weighs more than 7.3 pounds to be between 25 and 35%. So what if instead of weighing babies to the nearest tenth of a pound, we weighed babies to the nearest hundredth of a pound or thousandth of a pound, or we continued on with weighing babies more and more and more accurately until we measured them infinitely accurately? Essentially, what we would have is we would have an infinite number of rectangles between 5 and 9 pounds, and they would be infinitely thin. Those of you who have taken calculus would recognize this idea as an integral. And essentially, if we had an infinite number of rectangles between 5 and 9, and we asked something like, what is the probability of a baby weighing precisely 7.3 pounds? Well, then that would be 0. It's kind of like in a normal distribution, we never ask the probability that z is specifically equal to a given value like 1.8, because the area exactly above 1.8 would be 0. However, we can ask questions like, what is the probability that a baby's weight is between two values, like 7.3 and 7.5 pounds? When we do this, when we take something like a discrete random variable and we break it up into an infinite number of possibilities, we call this a continuous random variable. And in our example above, instead of being a histogram for a distribution, what we would have is a smooth curve to represent all the possibilities of the baby's weights. With a continuous random variable, we will end up with a curve similar to the one shown above, not necessarily the same shape, and you might recognize those as density curves that we studied in Chapter 2. Some rules about density curves: the probability of a given output value, or the probability of a given value, has to be greater than or equal to 0, and the total area under the curve has to be equal to 1. In this example, if this were representing the distribution of baby weights in pounds, the shaded area above would represent the proportion of babies born between 6 and 8 pounds, or the probability that a baby would be born with a weight between 6 and 8 pounds. So the only difference between a discrete random variable and a continuous random variable is that a continuous random variable can take on all possible values within a specific interval. So in the baby weight example, instead of only being able to take on values in 1 pound increments or tenth of a pound increments, the baby's weight could take on values any number between the minimum of 5 and the maximum of 9. Here's an example of a continuous random variable with the corresponding density curve, and if we wanted to know the probability of event A, then we would find the area above event A, and that would represent the probability of event A. And if the shaded area represents the probability of event A, the unshaded area represents the probability of the event A complement. One of the common continuous random variable distributions is a normal distribution. So let's do an example related to that. Suppose the heights of young women closely follow the normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. Choose one young woman at random and call her height y. Is the variable y a continuous or discrete random variable? First of all, some people are confused by this because they assume, since we can only measure to a certain level of accuracy, that it's a discrete random variable. That's a common misconception. Just because you can only measure to a certain level of accuracy, like the nearest tenth or hundredth of an inch, doesn't mean that it's not a continuous random variable. Women's heights can take on all values between the maximum and the minimum. So the random variable women's height is continuous. In part B, it asks, if you repeat the random choice many times and look at the distribution of y, the height values, what do you think you can conclude about the emerging shape of this distribution? Well, if we're doing good sampling and randomly sampling from a distribution of all possible outcomes that represents women's heights, then our distribution of our sample should start to look like that, and it should start to look approximately normal as we sample more and more. Part C asks to find the probability that a randomly chosen young woman has a height between 68 and 70 inches. So it would look like this. The probability that the random variable y, women's height, is greater than 68 inches and less than 70 inches is the same thing as converting it to a z-score by subtracting the mean, which is 64, and dividing by the standard deviation, which is 2.7. And we're going to pause for a minute, convert those to z-scores, and then we'll find the area under the normal curve between those two values. A reminder to you, when you're converting to z-scores, round the z-scores to 2 decimal places if you're going to use the table, because that's what the table does. And I'm going to take a minute and remind you how to do this on your calculator. So our random variable converted to z-scores of 1.48 and 2.22. So on our calculator, if we want to find the area under the normal curve between those two values, we hit second and the variables button. We go over and select number 2, normal CDF. We select our lower bound and enter that value, which is 1.48. Our upper bound, 2.22. When we're using a standard normal distribution, a z-score, when we've converted to a z-score, the mean is always 0 and the standard deviation is 1. We select paste, and then we hit enter, and this tells us that the area under the normal curve between those two values is 0.056. So this is approximately 0.056, or a way of interpreting that is approximately 5.6% of women have heights between 68 and 70 inches. So to finish up here, I would like you to take a moment and find these 3 values and interpret them in context. And this is what you should have found for each of these. The probability that a randomly selected woman is less than 65 inches tall is approximately 0.644. The probability that a randomly selected woman is 65 inches tall or less is approximately 0.644. And the probability that a randomly selected woman is exactly 65 inches tall is 0. Again, that is because when you think about a continuous random variable, there's an infinite set of outcomes from the minimum to the maximum. So the probability of a specific outcome is 0.